I want to do an example of the chi-square test for independence. As a quick reminder, there are three types of chi-square tests. There's a chi-square test for goodness of fit, which is if you took one sample and then categorized your sample in one way. For example, my table here, if all I did was took a sample of people and said, "What's your favorite sport?" then that would be a goodness of fit test. But I categorize here in two ways, their age and their sport preference. The chi-square test for homogeneity is you took multiple samples from different populations. So for example, if I said I asked a bunch of people under 30 what their favorite sport was, a bunch of people between 30 and 50, a bunch of people over 50, that would be a chi-square test for homogeneity. But in this case, I took a survey where participants were asked their age and what sport. So I took one sample and asked basically two questions. That's what makes this a chi-square test for independence. Sometimes those are hard to tell the difference between the homogeneity test and the independence test. Again, homogeneity said I took, in this case, maybe 3 different samples and just made sure basically I had groups in samples from each age group. But that's not what happened here. So at the 0.05 level, is sport preference independent of age? At least do I have that evidence. So I'm going to shrink this down a little bit so I have some room to write. For the chi-square test for independence, the null hypothesis is always that the one variable is independent of the other. So I'm going to say sport preference is independent of age. And my alternative hypothesis will be sport preference is not independent of age. That's my state. I should also just mention, if you were doing this like on the AP exam, part of your state should be stating which test you're using. Okay, maybe make a note that this should also be part of it. You should say you're doing the chi-square test for independence. Don't just say chi-square. Okay, the next thing I want to do is I want to make a plan to do this test. Let me fill in my row and column totals real quick. All right, I filled in the column totals, row totals, and the overall total. I only took one sample here. So the first condition is always that kind of 10% rule that I sampled all the public in this case, that I sampled less than or equal to 1/10 the population size. That's always condition 1. It is for almost all hypothesis tests. Now, condition 2, I'm going to write a little 1. Condition 2 is that all the expected counts are greater than or equal to 5. And I'm going to have to verify that that is true. The way we calculate expected counts in this case is we figure out where we kind of reproportion the amount of people in each age group equally amongst the sports. Easy formula for this is to, in each cell, you think about we've got kind of 9 cells in our table, to fill out the expected amount of football people under 30, we figure out the column total, 114 people here, and the row total, 125 football fans. We multiply those two and then divide by the overall total. So this one would be 114 multiplied by 125 and then divided by 338. Let's do just one more of those. This next cell right here, the 30 to 50-year-old football fans, column total 111, row total 125. So 111 multiplied by 125 over 338. Now, these expected counts would be part of our formula. You know, the chi-square formula, if we were going to do it by hand, is the sum of all of our observed values minus what we expected squared divided by what was expected. So in this case, we would do that with 9 different cells. we would figure out what this calculation actually was, and then we would do that calculation as our expected. So we do 51 minus that, square it, divided by the expected. So we'd have to do that 9 times. Thankfully, our calculator can do this for us. Along with the calculator running the test, it'll actually also give us our expected counts. So I'm going to come back to this idea that the expected counts are greater than 5. And let's go to the calculator. All right, I am going to put the table of information into a matrix. I've already had a matrix. You might not have one. But in my matrix, I want a 3 by 3. And I'm going to put in the information from the table exactly as it appeared, not including the totals, just the raw data from each of those cells. I'm going to put in here. Again, don't include the totals. You don't need to do that. That will be calculated for us. All right, we have them all. We're going to go to the Stat Tests menu, like always. We're going to go down until we see chi-square right there. I put my expecteds in A, or excuse me, my observed in A. The expecteds will be calculated for me and put in matrix B. And let's calculate. There it is, my chi-square statistic, 29.923, and that p-value is essentially 0. 4 degrees of freedom. I want to come back to that in a minute. But for the expected counts, if I were to go back to my matrices and just choose matrix B, say I want to see it, there's matrix B. And those are my expected counts. If I had done all the calculations, this would be those expected counts. And then we can copy this onto our page. So let me just shrink this down a little bit. And I'm not going to rewrite this for in the interest of time. But again, please make sure if you're doing this like on the AP exam or something, that you do indeed copy those expected counts onto your paper. It's worth it. It'll get you the points for it. So make sure and do that. And again, as a reminder, if you were doing this by hand, you would take each of your observed. So example, like here's 31. That would be your observed. The expected in that cell was 41.8. So 31 minus 41.8 squared divided by 41.8. But you would have to do that 9 times. So thank goodness we didn't have to do that. All right, the do step. We already had the chi-square statistic. It had 4 degrees of freedom. It was 29.92. The p-value, I'm just going to write that it was approximately 0 because it had so many zeros in front of it. The degrees of freedom, just really, really briefly, the degrees of freedom calculation is based on the fact that we count up the number of columns. We had 3 columns. And we count up the number of rows. We had 3 rows. We do 1 less than each of those. So degrees of freedom is the number of columns minus 1 multiplied by the number of rows minus 1. So basically 1 less than the number of categories in each direction. So we had 3 columns minus 1 is 2. 3 rows minus 1 is 2. That's why it was 2 by 2. To finish this problem up, I just wanted to go back and show my null and alternative. The final step of this, the kind of conclude portion, state plan, do, and conclude, I would reject the null because we had an extremely low p-value, much less than the 0.05 that was asked of us. So rejecting the null, I like to just cross that out, means we have evidence that sport preference is not independent of age. All right. To just recap this really, really quickly, we knew it was a chi-square test for independence because we only had 1 sample. Each person in the sample was asked 2 questions, but 1 sample from the population means it was a chi-square test for independence. Our null and alternative, the null is always that the one variable is independent of the other. The alternative is that they're not. In this case, I set up the preference would be independent of age. That's kind of the explanatory response relationship, I thought. The plan step, we verified that our sample size was less than or equal to 1/10 the population size. We also need all expected counts to be greater than or equal to 5. We could certainly do that using a formula, but we also could use our calculator to do that. We ran the test. We put the table in our calculator in matrix A, ran the test, got this chi-square statistic with a p-value of essentially 0. Remember, the way we get degrees of freedom is the number of categories in the columns minus 1 times the number of categories in rows minus 1. Don't forget to copy matrix B where the expected counts are put onto your paper. Finally, to conclude, well, we rejected the null because our p-value was so low. So therefore, we had evidence that sport preference was not independent of age. If this video helped you, please like and subscribe for more math help.